Hello, welcome back. Today we're going to move into section 5.4 and take a look at the fundamental theorem of calculus, which is going to lead to a quicker way for evaluation of definite integrals. That is quicker anyway than the use of Riemann sums. I'm sure we'll all welcome that. So we recall that the definite integral from a to b f of x dx is just a number. It has many interpretations. Again, depending on context, the one we're going to use most often is that if f is non-negative on an interval, then this integral is going to give us the area under the graph of y equals f of x and above the x-axis, at least over the integral from a to b. If the function takes on negative values, we can also interpret the integral as, sometimes we say the net area. This is calculated by thinking of regions above the axis as contributing positive areas and those below the axis giving negative areas. We then add these areas, add up the positives, subtract the negatives to get the net area. And there are applications, for example, like displacement, or when you calculate work done in physics, where these positive and negative parts really are very important. We saw an example of this use of negative areas to evaluate an integral in one of the previous videos, the one from section 5.3. Now, an integral is just a number, so the variable x that you see in the integral there does not appear in the answer. In this context, the x, which is often called the variable of integration, okay, is often referred to as a dummy variable. So it's kind of a placeholder, but it doesn't show up in the answer. Now, if we replace this dummy variable x by some other variable, the value of the integral is not going to change. So we can write integral a to b f of x dx, or integral a to b f of t dt, or integral a to b f of theta d theta, or any other number of different names for the variable. As long as the function f doesn't change and the interval of integration a to b doesn't change, these calculations will all give the same number. So we're going to make use of that because we're now going to start talking, we're going to kind of shift to the variable t, which will be handier notation in the future. So let's imagine an integral from a to b f of t dt and think about what happens when we change the value of b. So here might be the graph of a function. Here's our y equals f of t graph. And we can think of the integral, if we start at a and end at b as we did up there, as kind of giving maybe this net area if we want to give the area interpretation. Now, if we change b, we have a couple choices. We could let b get a little bigger, move it to the right. And of course, then we might be calculating further out here on the x-axis. If we let the b move that way, we see we're getting more negative area, and that's going to make the value of the integral decrease. So if you add negative numbers, things get smaller. On the other hand, if we slide b to the left, let b get smaller, and maybe stop the calculation here, then we are losing negative area, and so as a result, if we're adding in fewer negative pieces, our integral increases. So the value of the integral does change if we let this number b change up here. So we're going to start thinking of the integral now as a function of this number b. So the input is the variable b, which we're allowed to change, and the output then is the value of the resulting definite integral. And of course that output will change as the b changes. Now, we might be more comfortable if we don't use b as a variable. We're used to thinking of b as a constant, so let's change that variable name to x. So we're going to be studying in this video functions of the form given below. A function f that arises by letting this upper limit vary might be expressed this way. Capital F of x is defined to be the integral from a to x f of t dt. Okay. So over here, we've replaced the b by x, and again, we're imagining we can let this x change. And of course, as x changes, we're going to either gain or lose area, gain or lose distance, whatever the interpretation is in this case. So let's see, let's practice working with one of these functions. So let's take a function f of t. It's defined as 3 minus 2 times the absolute value of 4 minus t. Should have been an absolute value sign there. The graph of this function is shown below. We're going to define a new function, capital F, as follows. So capital F will be found by integrating little f from 1 to t. Now, I want to take note here that we want to be kind of careful about the variable in these contexts. We're using t as the dummy variable of integration. So it's the dummy variable. The x is something different. X is the input variable for the function. Now, it wouldn't matter here if I replace the t by z or theta or u, but I should never replace t by x in this context. I don't want variables playing two different roles. So when I talk about a function like this, if I have an x as the input variable for the function, I will never, and you should never, use x inside the integral. Always pick some other variable so we keep the variable roles separate. So that being said, we have the f, capital F, defined in this way. Just to practice, let's compute the values of f of 1, f of 5, and capital F of negative 1. So for part A, f of 1, so we just go over to our definition here. It says wherever you see x in the parentheses, you put that in the upper limit. So f of 1 is going to be the integral from 1 to 1 of this f of t dt. Now, as we saw in section 3.3, page 317, one of the previous videos, an integral with the upper and lower limits the same. That was, I think, rule 1 on page 317. That integral is defined to have value 0. And again, this makes sense because we can also interpret this as an area whose width goes from 1 to 1. So that'll just be a very thin area, a line of width, which is an area of region 0. Okay. Let's move on to the next one, number B. Okay, so now we want to do f of 5. And so the x is replaced by 5, so we're looking at the integral from 1 to 5, little f of t dt. So if we come over here to the graph of y equals f of t, the integral goes from 1 to 5, and we're going to compute the value of this integral by using our area interpretation. Or rather net area, because there's some area below the axis, some above the axis, and so this stuff below the axis is going to count as negative, and the stuff above the axis we will contribute as positive. Now this is a pretty regular shaped region, and we're going to find if we draw a little line right here, we can think of this region as two triangles and a small trapezoid. And again, since we know how to find the areas of those things from geometry, we can compute the value of this integral just by computing these areas. And that's what happens down here. Okay. So we've drawn in this little vertical line here to separate the pieces, and I've just, for example, plugging 1, t equal 1, into the function. You find the value comes out to be -3, and so I've put the -3 value down here to indicate the function value. F of 4 turns out to be 3, so that height will be 3. F of 5 is 1, so that height will be 1. And these horizontal distances, 1.5, 1.5, and 1 are easy to calculate. So that's everything we need to get the area of these three figures. And so our integral is equal to the sum of these areas. F of 5 will have, here's the area first of the lower triangle. I've gone ahead and just used the negative height in there, which is going to give us the negative contribution. So it's of height -3, width of 1.5. 0.5. There's the triangle area formula for that. Turns out this second triangle has the same area, but of course it has opposite sides, so those are going to cancel. And then here is the area of the trapezoid, and you can check that all this turns out to be 2. So f of 5 with this definition turns out to be 2. Okay, for part C, we have to recall rule 2 on page 317. This talked about flipping the limits on an integral. So putting in x equal minus 1 in our definition for f, we get the integral from 1 to minus 1 f of t dt. And if we want to put these limits in the more comfortable order of smallest to largest, we can invert the limits at the cost of this minus sign. And that's what that rule 2 is on page 317. So we'll focus on doing this integral instead. And again, we'll do that by areas. So the integral from minus 1 to 1 of f of t dt, we go from minus 1 to 1. Again, we can give this an area interpretation, and it's the area of this trapezoid that lies below the axis, and because it's below the axis, it's going to contribute a negative answer. I've indicated the heights, that is the function values at minus 1 and 1. And so this trapezoid has height of 2 and parallel sides of length 3 and 7. So if we do the area calculation, the signed area is given by this. We average the 2 parallel sides and then multiply by the height of 2, and that gives us minus 10. So to summarize, what is the value of f of minus 1? We saw f of minus 1 was this, put in minus 1 for x in our original definition, and then we flipped the limits on the integral, and then we just evaluated this integral here and found it was minus 10. So we have minus 10, or 10. So f of minus 1 turns out to be 10. So we want to be kind of careful with these integrals who kind of integrate backwards. So 1 to minus 1 means we're moving this way along the interval. And again, everything we've learned about with the fundamental theorem of calculus and so forth in our interpretations is for integrals where the limits are in increasing order. So if the limits are backwards like this, you might want to think about switching them at the cost of a minus sign, just to avoid the confusion. Now, one of the truly amazing things about these functions that are defined as integrals is that they turn out to be differentiable. And this is part 1 of the fundamental theorem of calculus. And here's that theorem stated. So we're going to state it for continuous functions. So let's let little f of t be defined and continuous on an interval I. Let a be a point in this interval. So we have just function defined on some interval I. And a is some point in here. Okay. And we're going to define a function capital F on I through a definite integral. Capital F of x is the definite integral from a to x. So the x will be somewhere else in this interval. Could be left, could be right. A to x, little f of t dt. And again, I've been careful to keep the variable of integration different from the variable x that is the input for the function capital F. Now, so again, if little f is continuous, we define a function this way, then the function capital F is differentiable on this interval I, and its derivative, capital F prime, or d dx f of x, or d dx of the integral from a to x f t dt, is little f. Wow. So we just got back that little f that was inside the integral. So this means the derivative of this integral function is the original function little f that we started with. In other words, capital F of x is an antiderivative for little f of x. Okay. Now again, the notation, details, variable names are very important here because f of x is a function of x. Its derivative is also a function of x, and that's why we write f of x here now for the derivative and not f of t. Remember, f of t is a dummy variable that doesn't really count in the integral because the integral comes out to be a number, or in this case, an expression involving x. So that's pretty cool, and this fact that functions defined this way by definite integrals are antiderivatives is going to lead to a very efficient way of evaluating definite integrals. Let's look at a couple of examples just to try this out. So let's define a function capital G as follows. G of x will be the polynomial 2x squared plus 1 times the integral from 1 to x of the quantity 1 plus the square root of the log of x cubed dt. So we're going to calculate g prime of x and then find the value of g prime of 1. So actually two problems in one here. I knew you were missing the product rule, so we made this thing into a product. It's this function, the polynomial, times the integral function, so we have to use the product rule. So in other words, you got to keep these things in mind. I could have made this a quotient too. So if we first of all apply the product rule, we find g prime is the derivative of the first function, there's the polynomial, times the second, which is the integral, and then the first function times the derivative of the second, so there's the integral differentiated. Now I compute the integrals of these two pieces. The 4x from differentiating 2x squared plus 1 is easy. And for this second piece here, we use the fundamental theorem of calculus, which says the derivative of an integral like this is just the integrand, that is the 1 plus root log t squared with the variable t replaced by the variable x. And so that's all there is to the derivative. There we have g prime of x. And notice it is a little complicated. It's a function. It has an integral in it. That's because of the product rule. And then we have this differentiated integral over here, which looks like the kind of functions we've dealt with in the past. So there's a quick application of the fundamental theorem of calculus, which allows us to, if we know that result, just take integrals like this and immediately write down their derivatives. To get g prime of 1, we can now just take this expression for g prime of x here and plug in x equals 1. So everywhere I see an x, I'm going to plug in a 1, so that'll be there, and here, and here. And that's what has happened down here. Notice the t is not 1, so I have to leave the t alone. The t is still in the integral. When I do this, I get 4 times 1, and then the integral from 1 to 1 of 1 plus square root of the log of t cubed. And then in the second part, 2 times 1 squared plus 1, and then 1 plus the square root of log of 1, because x is 1, and all that's cubed. And here again, we have the integral from 1 to 1. We know that that integral turns out to be 0. So this gives us 4 times 0, then plus what amounts to a 3 from here. The log of 0, the log of 1 is 0. And so this whole thing boils down to 3. So g prime of 1 is equal to 3. So let's look at one more example. A function h will define by h of theta is the integral from minus 2 to theta cubed plus 2 theta. And then we're integrating the function z over 1 plus z cubed dz. We're going to calculate h prime of theta. Now you probably guessed it. This is an example of the chain rule. So again, the chain rule, the product rule, quotient rule can all arise from working with these derivatives. So h here is the composition of two functions. One is the function, we'll call it g of theta, which is theta cubed plus 2 theta. That's the upper limit in the integral. And the other is the function defined by the integral itself. Let's call it f of u, which is integral from minus 2 to u of z over 1 plus z cubed dz. So then we can reconstruct h by taking h of theta equals f of g of theta. There's the g, there's the f. And notice this says the f says take what's ever inside here, the u, and put it in the upper limit. So that's how we get the g of theta up here through that composition. Now when we see a structure like this, we can apply the chain rule. H prime of theta is going to be capital F prime of g of theta times g prime of theta. So if we can compute capital F prime and little g prime, we'll have it. Those aren't hard to get. Of course, the g prime is pretty easy, just a polynomial, no challenge there. So g prime of theta is 3 theta squared plus 2. To get capital F prime, we're going to use the fundamental theorem of calculus. Let's start with f of u. So then f prime of u, or the derivative with respect to u of the integral from minus 2 to u of z over 1 plus z cubed dz, is by fundamental theorem. Again, we just get the integrand back with the variable replaced by this upper limit. So we're going to get u over u cubed plus 3. Now, we want f prime of g of theta here. So f prime of g of theta, now that we know what f prime is, f prime of g of theta, replace the u by g of theta, is going to give us g of theta over 1 plus g of theta cubed. And then if I replace the g of theta by what it is equal to, that's theta cubed plus 2 theta over 1 plus theta cubed plus 2 theta all cubed. So those are the pieces that go into this chain rule calculation. So h prime of theta is f prime of theta, f prime of g of theta, g prime of theta, as we mentioned earlier. And here is the f prime of g of theta, and that's multiplied by the g prime. And of course, we could do a little simplification perhaps, but since we weren't asked to, we'll just leave it at that. So watch for problems like this. You've got to know the fundamental theorem of calculus. It'll show up on the final exam. We'll do some work with it in class. And also, all the old differentiation rules are always in effect. Product rule, quotient rule, chain rule might turn up in any of these problems. So have at it. Have fun with this. Good night.